What's up, everybody? Welcome to Earth Science. So this is the beginning of the new unit. It's going to be fast. It's going to be 5 labs: minerals, igneous, sedimentary, metamorphic, and rock cycle. And it's going to be notes lab, notes lab, notes lab. So we're going to go pretty fast through all of this, but do what we can to make it easiest. Minerals is a good one to start with because when we get to rocks, like when you're looking at rocks like this, they're composed of minerals. All the building blocks of rocks are minerals. So that's what I had people write right up here. If you got these notes open, which you definitely should, what are minerals? I mean, there's the real definition, right? The building blocks of rocks. I'll make this all bigger so everybody can see it. Not that big. Slow it down. The building blocks of rocks. All I really said in here is that here's the definition of a mineral: naturally occurring inorganic solid. So naturally occurring, it can't be man-made. Inorganic, never at any point was alive. And solid, solid. You don't know what solid is. You're good. So, what your job's going to be when it's time for this? I redid this note sheet this year. See all these things that are like check marks with bold? That's going to be your job. You're going to get a box of minerals, and inside of that, you're going to carefully open it. A lot of these are brand new. The boxes are brand new, so please be careful. Inside of that will be a bunch of minerals that you are going to identify. All right, so the way I redid this note sheet was to say, okay, here's what this is. Here's what luster is. Here's what hardness is. But see how there's check marks with these big bold letters? That's what your job is. Okay, so as you're doing these notes, check mark, this is the thing. All right. It's also wise to get out the back page of your reference tables, which looks like this, the very back page. And if you need a link, go back to the all MP3 assignment thing. There's a link right there. The way that I set up the notes, the way that I really recommend you tackle the lab is to go in this order. What's the luster? We'll learn about that in a sec. What's the hardness? Does it demonstrate either cleavage or fracture? They do that with a check mark on this side of the line or that side of the line. Really, once you do those three, you're going to be most of the way there. Because if you grab this box of minerals and say, okay, I know what metallic is, there's some of those, the rest are non-metallic. And then you figure out the hardness and you put them in. The hardness goes in order here, from softest to hardest. And then again for non-metallic, from softest to hardest. And that, again, that alone is pretty much going to get you there. Then cleavage and fracture. And then maybe we'll get into what's the last little step we need. And that can be something that's in these two categories here. If you follow that method, you're going to be okay. All right. So what is this stuff? Luster is how the mineral reflects light. So you'll grab it and kind of twist it in your hand underneath the light bulbs and look and see how it shines that light. We're not talking color here. We're not talking clarity. Like clear is not a luster. This one's slightly transparent and see-through, right? But that doesn't have anything to do with luster. All a luster is how does it reflect light if I move it around underneath the lamps? Okay. Now, real life mineralogy, there's a whole bunch of those. New York State, Regents Earth Science, easy peasy. You only have to get 2 lusters. Is it metallic? Or is it non-metallic? That's it, right? So again, you pop them out of your box and you look. Shiny does not mean metallic. That one that I just had shines in the light, but doesn't look like metal. You'll see the ones like this that shine like metal. And you'll say that's metallic. The other ones are not metallic, and you'll be in good shape. All right, so there's one down. Do that when you get the minerals. And then take those, and I'm going to give you a great big one of these and separate them by the metallics at the top and the non-metallics at the bottom. Then we'll look at hardness, and that'll get you closer. The fancy definition, excuse me, for minerals is, for hardness, is the mineral's resistance to scratching. Which is to put up a fight against being scratched. There's this dude named Mose who came up with this hardness scale from 1 to 10. They're not it's not like there's no unit. It's not one something. It's a relative scale, and there's a mineral for each one of those. And again, in real life mineralogy, you would have to get it down in between two of those values. 1 is talc, 10 is diamond. So you scratch different minerals on them and you figure it out, right? Here, we're going to use, again, keep it easier. You can have one of three choices: less than 2.5, from 2.5 to 5.5, or greater than 5.5. That's it. Okay, so if it is softer than 2.5, it is softer than a fingernail. So take your fingernail. Got to be real fingernails. Make sure somebody in your group has real fingernails, not artificial ones. And try to scratch it. And if you can scratch it, that's great. Don't continue scratching it until the mineral is destroyed. One quick scratch, and you can say, okay, that one is softer than my fingernail. That one is less than 2.5. Or you grab one and you can't scratch it, nothing happens. Then you're going to say it's harder than my fingernail. And then the other tool you need, besides your own fingernail, is a piece of glass, and I'll have those in the supply box. So you'll take the mineral and try to scratch the glass, and nothing happens. So this mineral is softer than glass. Or you take it and it does scratch it, and am I missing one already? Here we go. Maybe you can hear it. Okay, that one makes a mark in the glass. It scratches it. So basically, your fingernail's 2.5, glass is 5.5. With those two tools, we'll put all the minerals in groups. By those. All right, and then again, that's going to put you on the reference tables like non-metallics softer than glass, non-metallics between the two, or non-metallics harder than the glass. And you're already most of the way done with the lab. Cool. Next is cleavage of fracture. How the mineral breaks. When you look at it, this is the hardest one, no doubt. When you look at it, I'm going to actually do fracture first. Fracture just means it breaks randomly. In all likelihood, everything you've ever broken in your life, a glass, some of my glassware in the lab, a plate, a bone, those just break randomly. Wherever the strain, expresses itself, boom, it breaks, right? Cleavage is when it breaks along parallel planes, and planes, like flat surfaces. So when something like this breaks, see how it looks like a perfect parallelogram here? That's like this kind of cleavage right here. Okay. I don't know what I did with the names, but either way, whenever this breaks, and we're not going to do this, but if I took a rock hammer and smashed this, I would just smash it into smaller versions of this parallelogram. Okay, so if you see multiple parallel flat faces, you're probably talking cleavage. If it just looks like this just looks like a hunk of rock, I don't see any flat faces parallel to each other, that's fracture. Maybe tricky, I'm here to help, okay? And on the reference tables, there will just be a check mark on one side or the other, whether it has cleavage or fracture. And some, honestly, given the quality of the specimens we have, like spotting the cleavage on talc, which is in your box, is very, very difficult. I can help with it, but not easy. So that's that. All right, so the rest of these are going to be ones that are like less valuable, but might be the things that give you like that finishing touch. So streak, what you're going to do is rub the sample once on a streak blade. What I'll have sometimes people do is like, you don't need to do that. Take the mineral and one time, just like that. Okay? I have black streak plates and white streak plates. You'll have both, because if it's a white streak, it's hard to see on a white streak plate. Vice versa with black one, right? Some won't have any streak if they're very hard. That's fine. And what it does is it powders the mineral. This is basically like a ceramic tile, like a bathroom tile, but it's unglazed. So it's very, very finely porous. So it powders the mineral as you rub it on there. And you're identifying the color of the streak. Maybe it's useful, maybe it's not. Some are a big giveaway. That one has a red-brown streak. This one has a green-black streak, and so on. Other ones, if it doesn't list anything, it's probably not really a very distinguishing characteristic. It's not super strong. But we'll do it anyway, and it'll help for some of them. Same with these. like these are maybe the one that can like tip it between two, or maybe it's a dead giveaway right from the beginning, but it's not really a test you would do right at the beginning. Um, Color, not super useful. There's lots of minerals that are white and gray, or there's some minerals like quartz that can have multiple different colors, so the color doesn't help at all. But maybe you got it. Geez, I'm down to like it's either this one or this one, and this one says that it's uh, green, and this one says that it's red. Maybe it helps right at the end tip the scales one way or another. Does it smell like rotten eggs? A lot of people know what that is. It's this one, especially if you scratch a little bit. It smells like rotten eggs, and that'll be a good giveaway. Um, Density, you're not going to actually have to like measure it, like go get the scales and do displacement and all of that. But like, does it feel when you put it in your hand? Give it the just, man, this feels a little hefty. This feels like unnaturally heavy. Maybe this one just feels. Actually, this one feels pretty light, and others feel, just about right. Again, that's not going to be something you need to do for all of them, but maybe it's a giveaway. When you like rub it with your thumb, what does it feel like? Some have kind of like, it sounds gross, but like a greasy, smooth feel. Um, you'll see. Magnetic. There's a magnetic one in there. It's magnetic. And when you get the magnetic one, you're going to say, boom, that's magnetite. I'm done with that work. Acid tests. I'm going to try to find some acid and demonstrate. Don't worry, the minerals you have will not have acid dumped on them. I'll do that separately. As soon as I can find some acid. All right, that's it. That's going to get you through the slab. I do want to do this little blurb right here real quick, but if you go in this order and then fight through the reference table in this order, this lab could be a breeze. I'm hoping that it is, because then we got to go into the next one, into the next one, into the next one. Real quick, what gives minerals their shape? And then possibly whether there's cleavage or fracture. It is the internal arrangement of atoms. How do the atoms, like there's chemical formulas here, right? The famous example of this is halite. Halite is NaCl. If you ever need to know what those are, they're down here. Sodium and chlorine, right? Sodium chloride is the name of the molecule. The way that sodiums and chlorides like to interact because of chemistry, things you're going to do next year because of the type of bonds that form, is they like to grab each other at like a 90-degree angle. So here's what, 9, 18, here's 27 atoms of sodiums and chlorides that all grab each other in a cubic pattern. We'll take a couple billion atoms, and all you do is you go from a very tiny cube to a larger cube, and that's it. So from the smallest form to the biggest form, salt likes to form cubes. And if I get a big chunk again, they've been hard to find lately through the science catalogs. We'll do the demo where I can get one like this big. I used to be able to get them. And you smack it with a hammer and you get smaller cubes. Then you smack it with a hammer and you get smaller cubes. And you smack it with a hammer and you get smaller cubes. Always cubes, always cleavage like that, because of the internal arrangement of the atoms, because of the way that the atoms are arranged. So that happens like in tetrahedra, that happens like in sheets. You'll have this guy here. Look how thin it is. They're sheet silicates, they're called. Their form of cleavage and the way that the atoms like to hold on to each other is out in sheets. And then you just get stacks of them. But those stacks aren't very well bonded. You can just literally pull these right apart. Some are like tetrahedra, little pyramid shapes, right? All because of how the atoms are shaped. So the shape of I'm going to go molecule that makes up that mineral, determines the shape of the mineral, and can lend itself to determining cleavage. Sound good? This thing pops up once in a while. I wouldn't say it's a huge deal, but fighting through the reference table is where we're going with this thing. All right? You can do it. Good luck, everybody. Thanks for tuning in. So long.